Okay, in this video I want to continue this discussion of integration by parts, but now looking at inverse trigonometric functions. This happens to be another powerful use of integration by parts to integrate inverse trig functions, and next we'll see logarithmic functions as well. Now these are slightly different than the pattern that we've been seeing, and that's because you don't have a product here. You only have one function. And so we'll take a look at how we handle that type of situation. Now it turns out that according to Lippitt, we first look for logarithmic, then inverse trig. So we want to use the inverse trig function as our u. So u would be sine inverse of x, then dv is going to be whatever's left over, and that's just the dx. So we can differentiate sine inverse of x. We know that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared dx. Now v, which is the integral of dv, which is just the integral of dx, is simply x. We recall our formula. The integral of u dv is equal to uv minus the integral of v du. So integral u dv would just be integral sine inverse of x dx, which is what we're trying to find, and that's going to be uv, which is x sine inverse of x, minus the integral of v du, which is the integral of x over square root of 1 minus x squared dx. And we'll put this all together now. So uv is x sine inverse of x, then minus the integral of v, which is x, then times 1 over square root of 1 minus x squared, and dx. So that doesn't look a whole lot nicer to integrate. It happens to be good though, because we should be able to use U-substitution with that integral, and that's going to help us out there a lot. Now one thing about using U-substitution with integration by parts is that we're accustomed to using u, but u and v have already been used, and so it makes it a little awkward there. But we're not actually going to use u and v in the actual expression once we put it all together. So I think that it's okay if we go ahead and use u again, but in a different way. I hope that's clear. At least I'll use a different color for it. And so our u here is going to be 1 minus x squared. And du then would be negative 2x dx. And what I'm looking to swap out is the x in the numerator, dx. So I can say that x dx is negative 1/2 du. Now my denominator is square root of u, so I'll write that in the numerator as u to the negative 1/2. And so simplifying, I still have x sine inverse of x, then it's minus the integral, but I'm going to have the minus from the negative 1/2, so that's going to become plus 1/2, the integral of simply u to the negative 1/2 du. And when I integrate that, I'm going to get u to the 1/2 over 1/2, or 2 times u to the 1/2. So I'll continue on the other side. I have x sine inverse of x plus the 1/2 times 2, u to the 1/2 plus c, and the 2 and the 1/2 will cancel, and I'll simply get square root of 1 minus x squared. So the final form is x sine inverse of x plus the square root of 1 minus x squared plus c. Okay, and I'll leave you in integral of tan inverse of x dx. And you can pause the video and come back for the answer and have it worked out. Again, so u is going to be tan inverse of x, dv is dx. du is 1 over 1 plus x squared dx, and v is just x. Our formula, integral u dv, is uv minus integral v du. And we'll move that out of the way. uv is x tan inverse of x, integral of v, which is x, du is 1 over x squared dx, 1 over 1 plus x squared dx. We're going to do u substitution, a different u, remember. u is 1 plus x squared, du is 2x dx, and x dx is 1/2 du. So we have x tan inverse of x minus integral u to the negative 1 du. And that integral is going to be the natural log. But we're out of time.